Okay, well, thank you everybody for joining in to our January speaker series from the Rochester chapter of IS&T. I'm Roger Triplet, president of the organization this year. But for today, I'd like to thank Julie and Patrice for volunteering to give a presentation today. They are both employees of Immervision, based out of Montreal, hence our online meeting. I went to the website about Immervision. I see that their mission is to develop eyes for machines. They're helping machines see the world better. And I also learned that they do a lot of wide angle imaging, which is something Julie, I believe, is specializing in. And they've coined a term panomorph lenses. I'm very interested to hear what that's all about. Patrice is a co-founder and vice president of technology, and Julie has been a research scientist developing wide-angle imaging pipelines. So with that, their presentation today is about flexible simulation pipelines for vision systems, early validation and optimization. With that, I will turn it over to Julie and Patrice.
Thank you.
Thank you, Roger.
Thank
you very much for the intro. Yeah, just just to say that Julie did the most of this work, so I will give most of the mic to Julie and all the credit. What I would like to say is, because we have this conversation just before starting the talk, so Immervision is a private company, and we design vision systems since 25 years now. We came with this idea of panomorph optics, where we can create an augmented resolution area in the very wide field of view. That was the foundation, and through this journey of 25 years in imaging, we collaborate with universities. That's why you can see the Laval University logo on this slide, because we like to first do fundamental research. We like also to the IP and making innovative IP, and as well as we like also to validate our work and publish our work to academia. So that's why you see all those logos. And this idea of simulation pipeline came from working with our customers. And the question of our customers was always, before investing very hard time and deep money in a new custom vision system, could you predict the outcome of this vision system before starting spending a lot of time and money? So that's why we developed this pipeline, helping us to answer to those questions and giving them confidence of what will be the outcome of their product. And it started by human vision, and it was important at that time to predict, okay, what will be the sharpness of the camera? Will it behave good in low light condition? But it was even more important now with AI, and computer vision, where sometimes the algorithm are difficult to predict the result depending what the human can see in the image. So that's why we developed this simulation pipeline, simulating each component in the vision system. And our goal was always to reduce risk for customers, reduce cost, and also reduce the time invest in the development of their product. The solution has, of course, a few limitations, and what I can say is we are investing a lot of R&D in polishing, developing, and adding some component in this simulation pipeline. So this is a moving work. So what you will see today is the most recent contribution. But you can stay tuned, and you will see at the SPIE some new development in the coming months and years. Now I will give you a kind of overview of what is this simulation pipeline and what we propose in terms of different components in the simulation. So basically, the idea is to start by the scene, and we start by what we call the 360 scene, so very, very wide field of view capturing the complete environment of the scene. And we simulate the different components of the vision system. So starting by the field of view of the lens, then we add the distortion. If you remember, that's one of our DNA, like we control the distortion to magnify some area of the field of view. So it's very important for us to be able to simulate this distortion of the lens. Then the sensor field of view, the different optical aberration, and then we move to the sensor. So with simulating the noise according to the illumination, and then moving to the ISP. So how the debayering algorithm impact the image, then the color, and at the end of the pipeline, we are either able to look at the image, measure I would say, the human vision KPI that we know for a while, but we are also able to plug a vision task at the end of the pipeline and see exactly what will be the performance of, I would say, a 3D reconstruction or object detection algorithm based on all the parameters of the vision system. And we can then change those parameters and see the impact in real time on the vision task. So it's super helpful to define, do I need to increase the field of view? Do I need to increase the resolution? Is there an impact from the sensor in low light condition with the noise? So all those questions can be answered with the software. So Julie, I don't know if you want to add something on top of that. Don't hesitate.
Just a little addition about our pipeline is something we really focus on is that we don't necessarily require to have the complete design of a component to simulate it. Because so if you have, for example, a complete optical design, for sure we can simulate it. But if you just have application KPI and you don't have the full optical design in mind, we can already simulate and adjust the specifications. So we really build the tools in order to help translating application KPI into component specification. So we try to build not like the most deep physical tool, but maybe a tool a little bit simpler and that require less inputs.
Could you say a couple words about the how is the scene modeled? Is it scene modeled? Is it simulated? Does it start from some high resolution source?
So actually we have both. So in this precise example and most example that will be in the presentation, those are high resolution real image. So for that, we benchmark all the 360 camera on the market and choose the one that permit us to have the most perfect image as an input image. So here it's a real image, but we also develop for scenes that are more challenging to capture. We also use a synthetic image. For example, let's say for defense application, we create synthetic image to start the scene. So really have both. It really depends on if you really want to have the most accurate, let's say, MTF measurement at the end of the pipeline, you might prefer to use synthetic image. So you avoid any type of pollution on the image. But if you prefer a more realistic content, just maybe to validate the overall aspect of the image, the real scene will be more pleasing and realistic. So we offer both.
I have a question.
Yeah.
Yeah, I see from the various steps here, you're correcting for the debaying, the demosaicing, and also color processing. So my question would be, do your clients or potential clients expect you to simulate their processing, for example, their pre-processing, like any distortion correction or color processing?
So for all the blocks that we have here, basically we can either provide the default algorithm, like we in our tool, for example, the ISP block with the debayering and color reconstruction is really basic. Like we have a little bit of edge enhancement, denoising, but nothing too fancy. But we enable the user to kind of plug its own algorithm on it, so he can directly insert what he already develops.
I see. Okay, thank you.
So now that you have an overview of the tool, I will just give you a quick vision of the presentation. So in the first part, we will see how we could validate the accuracy of our simulation. And when I say validation, it's comparing the final image quality that we obtain with nominal data, but not only nominal data for a design, also with physical module that we brought to production, and how we use this validation to really understand the impact of manufacturing tolerances in the simulation, how we use that also to identify the most impactful features that are really mandatory for the simulation. And in the second part, I will present you a few use cases that we had in the past to really highlight all the different aspects of the tools. So I think we'll try to spend most time on the use case. I think it's more interesting, but we'll start with the validation.
Julie, just before you move to the next slide, we have a question from Nicola. Do we modelize or simulate the motion blur? So I know the answer, but I'll let you answer.
So right now we do not simulate the motion blur yet. So yeah, this is a never-ending improvement of the tool. We have many features on our roadmap. Motion blur is one of them, but not yet, unfortunately. Okay, so for the validation part, just quickly, I will show you the pipeline that we use to simulate, to do the simulated image that we will compare with a real image. So we started, we used a chart from Imatest to do the image quality measurement. This is a vectorialized version to avoid any type of image degradation. We inserted this chart into a 360 scene, and then so we could choose the distance of the chart, for example, the location in the scene, and then we render the rectangular image that we use as an input, as you saw earlier. And then we apply step by step all the different blocks. And so at the step of the optical image, we can compare our simulation of the optics with the real optics. And then at the step of the sensor image, we can compare the overall system MTF with the physical module, and also compare the noise level measure on the simulated and real image. Just for this presentation, it's a monochrome sensor, but we will talk about the color aspect in the use case later. So we did not evaluate the demosaicing, for example, for now. So now that we saw how we did generate the simulated image, we compared this with different data. So the first one is we compare the obtained image quality with the nominal design. So basically the one that the performance that we see in our optical design software. Then we also compare the image quality of the optics with the one that we measured in Laval University lab using a device called lens check from Opticos. So like that, we can really isolate the effect of the optics on the MTF. And finally, we compared the overall image quality by comparing our simulated image with a real image taken in our lab. So we have an image quality lab in which we can control the lighting, the environment, so we can really be accurate in our measurements. So this is an example of what the simulation looks like versus what the real image look like. And so then we use that for our results. Here you can, here we will focus on the MTF measurement for the optics only. So first we simulated our optics using the nominal function that we extracted from optical design software only. And when we measured the MTF 50, we can see that we have a deviation from the data of the nominal design of 5%, so 0.02 MTF, which is way below the manufacturing tolerances announced by the manufacturer of this lens. And the only problem is when we look at the deviation to the real module, so when we measured the MTF of a physical module with a lens check, we obtain a deviation of 11.5%. Actually, it's still below a module-to-module deviation, but it's a little bit increased. So that's made us consider using tolerancing data in our simulation. So because of those results, we decided to insert Monte Carlo simulation on the optical design to be able to take into account the manufacturing tolerances. So here, what we did is we generated 20 different designs out of the same nominal data, and we chose like the median one, so really the one in the middle. And when we compared to the real module, we managed to lower the error down to 4.8%. And as you see, like the manufacturing data show that the deviation from a module to another can be up to 20%. So in a practical case, we can totally use this simulation to do evaluation of pre-evaluation of the design. So this type of measurements validated that our simulation is accurate, but most importantly, it validates that if you really want to get closer to the real module instead of the nominal data, like manufacturing tolerances are key to be integrated in the simulation. And this is also a good way to choose if you want to generate an optimistic or a pessimistic simulation depending on the use case. So this is the simulation that I just showed. The result that I just showed were done with a simulation in which we assume that we have access to the complete design. We really extracted all the data that we needed, so it was the most ideal situation. But let's say that you are still not sure of the design you want to use, you just have application KPI. Can you still simulate accurately the final image? So we developed another option in the tool, which is to only, for the optical aspect, to only enter MTF values across the field of view for different frequencies. And we developed an algorithm that automatically estimates the PSF out of those MTF values. So for the same design, this is what we obtained. So on the left and the right, you have the tangential and sagittal MTF measured at different frequencies. So the first column shows the MTF measured on the simulation, and on the middle column, you have the results. You have the target MTF that we wanted to reach. And so you can see that the errors measure with this simplified simulation are still in the same range. We are still, they are a little bit higher than in the previous case, obviously. But you can see that we can still have an idea of the final image quality, even if we don't have the complete design in our hands. So we can start to adjust some optical parameters, even if we don't have a lens design in our hands. And finally, for the validation of the image quality, we compare, so right now we just consider the optical MTF, so the image degradation due to the optics, but actually the sensor plays a huge role in the MTF of the overall system. So we compare the MTF of our final image, including the sensor simulation, with the real image that we capture in our lab. So for that, we use IMATEST measurement for the MTF. So we have this kind of graph, and this is the error, the average error that we get across the field of view. So this is the average error. Interestingly, it was kind of constant over the field of view. It does not, there is no more error at the edge of the field of view. It's pretty constant. And so you can see that for the overall image MTF, we are also below the range of module to module deviation in terms of MTF errors. And also, so we run this simulation for different illumination level. And we can see that we are pretty consistent with the illumination variation. And to finish with, I don't know if still, you can interrupt me if you have questions, so don't hesitate. But
I don't have a question, Julie, but I have a remark. Maybe you will cover that in the next slide, but the case where we don't have the design and we don't know what will be the camera, what will be the sensor, which MTF we need, that's the most, I would say that's the one that we face the most, starting at the beginning of the project.
Yeah.
To reassure customers that we can deliver good quality. Then all along the project, the customer asks us, okay, where are you in your design compare of what we commit on? So we can, with this as well, they can follow the progress of the design with real image instead of I would say, numerical KPIs. So all along the specification, design, prototyping, and production flow, this tool is used to communicate with customer and validate the outcome of the vision system. Just a remark.
No, that's right. And basically, you believe what you see, so it's always more convenient to have an image to prove that this is the best design than just showing MTF values.
Yeah, I had a question. You were mentioning that including the sensor in your simulation was important. Perhaps you're going to go into that, but can you describe the elements of the sensor simulation, the fill factor, or sensitivity profile, or things like that included? It looks like you're including exposure and noise. Am I right?
Yeah. So actually, I think this is just the slide after where you can see the used input for noise simulation.
Aha, okay.
So yeah, basically we take a few information from the scene. So we assume for now a global illumination, so a constant lux level for the scene. We take into account exposure time, different aspects of the sensor from data sheets. So we have the digital gain, we have all the well depth information, the quantum efficiency, of course. From the scene, we also take the charge reflectivity, which is also really interesting to have, and the light source spectrum. And this is the ideal input information. Of course, when we have an image, sometimes we do not have the reflectivity of the scene. We do not necessarily really know the exact light source spectrum. Same for the quantum efficiency of the sensor. Sometimes we just have single values, while sometimes we have the full spectrum. So in our tool, we make sure that if you have all of this information, you can input them, and it will be the best simulation. But if you don't have those information, we provide default values based on our past experience with sensor, like what would be the most probable characteristics. So you can really, you really have different level of accuracy. I don't know if it answers your question, or if you want more details.
No, that's fine. I actually was thinking of the effective profile of the sensitivity across the sensor might have effect. Essentially, it's effective point spread function, but that may be beyond a lot of information that you would have, I think.
Yeah, and it's and actually for the sensor simulation, that's something that I think this is the most challenging part of the simulation, because it's really hard to get all the data that are necessary to really render the most accurate image. So still with those input that we used, we're able to measure the SNR on the gray, on the background of the chart, on the gray, light gray area of the chart. So we compare the real and the simulated image. We take the average SNR, and we see that at 10 lux, the deviation in decibel was below 1%. So less than 0.5 decibel on the noise level for at 10 lux. So we are pretty close to the real image. Then we also made sure that changing the illumination level didn't affect the simulation accuracy. And as we can see, like we are still we are also accurate at 100 lux, and we do not degrade we do not increase that much the error at 10 lux. So as I was saying, the noise part is really challenging to simulate, and we still have a few aspects that we need to work on. We really have a lack of information from the vendor. For example, for the readout noise, we have an implementation ready. We just struggle to find the data for specific sensor. We still have a fixed pattern noise implementation, which is not included in the current tool, but is in progress. We are working on refining as well the HDR simulation. So we still have some ongoing work on that part. And so if there is no question on the validation, I think it would be nice to switch to so this is just a quick summary of what we saw, but I think it would be nice to switch to the different use cases that we met in the past. And so just a reminder of the biggest outcome of this validation step that we did. So we really realized that including manufacturing tolerances in simulation are really key to simulate realistic physical modules and not only nominal designs. We also proved that we do not need to get to have access to the complete design to start the simulation. Only KPIs such as sparse MTF values can be sufficient to already have a clear idea of what the image will look like. And so, the last point is maybe a little bit less relevant, but we show that our simulation is robust to different lighting conditions, light sources, etc. So for the use case, so there will be different aspects covered. The first one will be the validation of a camera module that we made for low light navigation. So to introduce this first use case, our objective was to design an ultra-wide-angle miniature camera for low-light drone navigation. So the KPI was to be able to develop a lens on which an obstacle detection algorithm would perform the same regardless the illumination. So we need the same accuracy during daylight down to 1 lux. What we started to do, so the initial KPI that I just explained was also mentioned, like, okay, I want to be able to detect a tree, like a branch on a tree at 50 meters, for example. We had this kind of requirement that helped us defining the first lens specification. And then we were able to design a lens optimized for low light that was 190 degree of field of view. And then the thing that I want to focus on for this presentation is how did we choose and validated the sensor. So our lens performed really well for low light, but what sensor should we choose and will the sensor work? So for that, we started by just looking on sensor datasheets, and based on the constraint of the use case, we needed to choose a sensor with reasonable pixel pitch. We had size constraints. It was a camera module that is supposed to be carried on a drone, so we have some size constraint. We also wanted the biggest resolution possible in order to maintain a high image quality, even if it's a super wide angle lens. So we managed to find some appropriate sensor with a 5 megapixel resolution. And the goal was to validate if this sensor would actually enable us to maintain the obstacle detection for all the range of illumination. So for this part, we use our simulation tool. First, we simulate the lens associated with the sensor. We apply a basic ISP, which is simply demosaicing. We obtain this type, so this is an example, an image for an example image. And you can see that you can clearly well detect a bird in the sky at 100 lux. Then we tested lower light. We still detect the bird. We can see that the confidence score is lowering, but we still have a detection. Finally, we went down to 1 lux, and not only we missed the bird, but also we start to hallucinate some objects, like a big object apparently, and due to the biggest quantity of noise. So thanks to this study, we could see that the sensor was not really matching all of our requirements, but it was still not too bad. Like we could manage to go down to 6 to 7 lux. He had a good form factor, a good size, a good weight. So what we did is we slightly tuned the ISP. We added some software solution to reduce the noise. And with our custom ISP, we resimulated with the custom ISP, and we obtained those results. So as we can see, we managed to, even if it lowered the confidence score for higher illumination, we still have a pretty good confidence score, and we still detect the bird. And this time at 1 lux, we were able to really well detect the bird by enabling this denoising in the ISP. So thanks to the simulation, we're able to validate that the sensor would be a good fit for our problem, but also that it could be a good fit only if we fine-tune the ISP and add some denoising. So because, thanks to this study, the sensor was validated, and then we could revalidate with a prototype, but we didn't lose too much time doing trial and error, waiting for prototype to validate this. And in the end, the same result was observed with the real prototype, the physical prototype. So this is the example for sensor validation. Then can show you another example where we determine the optical specification of a lens for a specific problem. So this for this use case, the objective was to design a wide-angle lens for autonomous driving. And the KPI was to maximize object detection at the edge of the field of view. Because usually we can well detect what is happening in front of us, but it's more challenging to detect objects on the side, especially with wide-angle image on which the distortion tend to degrade the detection of objects. So yeah, and then that's why one of our constraints was that we couldn't crop the field of view or do distortion rectification for this lens. So we needed to find the optimal distortion curve that would maximize the performance of an detection algorithm without any post-processing rectification. So here, what I will show is different examples. So we designed different type of distortion curve. So you have one linear one. The orange one will show an increased pixel density at the edge, at the center, and the green one at the edge. And we simulated the lenses. So all the other parameters were the same, and we only changed the distortion. And we obtained those images. So this is the same scene, exactly the same scene, only the distortion changed. You can see the same field of view. And so you can quickly see that if you really want to maximize the chances of detecting cars, here it's car, at the edges of the field of view, you can see that the last image will be better because it will not only detect the cars, but also provide a really high confidence score. So it will increase the detection rate and decrease the hallucination rate compared to a lens distortion with an augmented pixel density at the center. So this is the central image. You can see that you also miss the car at the edges. And for the constant image, for the constant pixel density, so the image at the left, you can see that all the cars are detected, but the confidence score is way lower on the edges, which might lead to missed objects on other situations, more challenging, maybe at night or something like that. So thanks to those different simulations, we can really quickly, like almost instantly, verify that we needed a distortion curve with a pixel density augmented on the edges, and we could export and give this distortion curve that we design on the tool to an optical designer to start the real design of the optics. So once again, it really helped us saving time. We didn't have to build a prototype to test. We could directly rely on the application KPI. We were sure that this distortion curve will guarantee the results for the detection algorithm. So it really helped us for this project. So still again, if you have questions, don't hesitate. Otherwise, I will switch to the third use case. So the first use case is oriented toward the image quality tuning. Right now, once we recover the image on the sensor, we use the mosaicing algorithm to recover the color image, which usually present a greenish shade, like the one that you can see on this image. And actually, what is done currently to recover nice and pleasing colors, we capture a lot of images of the chart with the camera in different lighting conditions, inside and outside, etc. And for each of them, we will do a color association between a target and between the color patch on the target image and the one that are captured with the real prototype. And then through an optimization process, we will be able to estimate a color correction matrix to transform the initial color into the target color for all the patches. Because of the amount of colors and the amount of light sources, this is really time consuming. It's also high cost, like most of the time, you have to recapture the image several times, like there is always one of the patch which is saturated or the image was not exactly taken the good way. So this is also high cost. And also importantly, it cannot be done. This color correction algorithm cannot be developed before having a camera prototype in your hands. Like you are really blocked, so you have to wait the lens design to be done, the sensor to be chosen, the prototype to be built, and you can also not kind of predict if you will be able to compensate some of the default of a lens, for example, with the ISP. You have to build the first part of the system and then tune the ISP. What we did is that we used our simulation pipeline to save us a lot of time once again. So we simulated almost instantly very different images of the same chart, but with different light sources. So as I said, indoor and outdoor, under different illumination levels, etc. And we run the color correction matrix calculation on those simulated images. And so this was doable before having access to the physical module. And thanks to that, we're able to start the image quality tuning before having a prototype. So really, we could start this earlier in the project. And this is how we manage now to compensate, let's say, defaults on the hardware with software. And so like that, we really better make all the components communicate in a more efficient way. And so just to show you the results. So here is the images that we simulated versus a real one for one of our camera module. So before color correction. And what we did is we calculated a color correction matrix for both real images and simulated images. And then we applied the 2 color correction matrix calculated on the real image. And these are the corrected images that appear here. And as you can see, they are not identical, but they are pretty much, they are very close. You can see that maybe for the simulated one, you have a brighter yellow patch, for example, but nothing that you can correct afterward during the fine-tuning of the algorithm. And just to give you some more precise data, when we measure, still on ImaTest, the color deviation between the 2 images, we managed to reach a pretty low deviation of 1.73. And we also measured the gray patches deviation, so only on the bottom line of the chart. So these are the patches that we use for white balance algorithm. And we found out that the deviation between the simulation and the real patches for the bottom line was lower than a module-to-module deviation. So also this showed us that we can totally use this simulated image not only for color correction, but also for white balance algorithm training. And we also measured the color deviation for the rectified image. Here it's still it's a little bit increased, but and this was for the proof of concept. We still have a lot of data to generate to customize this this algorithm.
Excuse me. I think we have
Yeah.
a couple of questions in the chat. Somebody can read them, or I can.
Yeah,
I
because
can
I
take care
don't
of
see.
it. Yeah.
Sure. So the first question was, do you have reflectance spectra for the patches of the color checker
Yeah.
chart? Yes.
Yeah.
And the second one, I think is yes, but by color deviation, do you mean a delta E 2000 or delta E? It's a CLAP error, no?
Yeah, it's the delta C00, like the one, I don't know if you see at the bottom of the right image, the one which is underlined in
yes.
red.
Okay. Oh,
Were there other questions? Or?
Nicola has another question. I don't mean to be a spokesman, but anyway, where did you get the reflectance spectra? From a public database or direct measurement?
No, actually, we asked the chart vendor. So he agreed to share those data with us.
Very good.
And just to follow up
But
one more, please.
Yeah.
What assumptions do you make about the spectral quantum efficiency for the red, green, and blue? What sensor do you assume? Because obviously, I think you're trying to model a generic sensor, but you're trying to apply this to a particular potential product. Is that correct?
So can you repeat that? Not sure I got it.
So there were some questions about the spectral reflectance of the color checker. But in addition to that, the quantum efficiency of the red, green, and blue channels of the sensor.
Yeah.
And so, what assumptions do you make about that, or do you have that spectral data as part of this process?
Yeah, we have the spectral data in the process.
Okay. Thank you.
Okay. So, any more questions, or? I think it's fine. So we will switch to the last use case that I wanted to present today, which is also another type of validation. So it's still an automotive use case, but what we wanted to create is a lens that is able to maintain performance despite camera degradation that can occur during its lifespan. So for an automotive camera, especially where we are based in Montreal, a camera can be exposed to really big temperature changes during its life. And because of the mechanical assembly of the camera, this can cause a defocus of the lens. So this will degrade the image quality. And we wanted to evaluate for our lens design how it would affect an object detection algorithm for different temperature. So what we did is that we simulated different for the same lens. We added on top of the lens performance different amount of defocus. So here you have the amount in microns. And we applied those transformation on the same data set. So we had a different data set for different amount of defocus. And we run the same AI algorithm for detection on all those data sets. And you can see on the graph here the performance of the object detector as a function of the defocus. And what you can observe, and which is interesting, is that especially for the F1 curve, which is the most relevant, you can see that you have an amount of defocus that will not affect the detection. For example, if you go to 6 micrometers of defocus, you only lose 0.6% in the performance. And if you go down to 10 micrometers, you only lose 2% in the performance. So for some application that can be critical, but 2% can still be acceptable, and 0.6% is definitely acceptable. And what we did then is that we estimated, well, this is a very basic thermal model, but we estimated what would be the temperature change corresponding to this amount of defocus for this lens. So I will go quickly on the formula, like we don't really care about that, but what we managed to show is that 10 micrometer of defocus was corresponding to a temperature shift of 43 degrees. So that can be a lot, depending on where you live, but that's something that can happen to an automotive lens. And so thanks to this simulation, we're able to know that the camera, like the initial performance for object detection, could be degraded of 2% due to those temperature changes. So we could really monitor the camera during its lifespan thanks to this type of simulation. And that was the last use case. So you can see here the analysis that we did. We were obviously curious of why we can tolerate this defocus, how did the performance evolve. So we noticed that because of the defocus increasing, what we miss are mainly objects on the edges of the field of view or in dark areas, but we still maintain good detection in front, in the middle of the image. So this is a video showing this kind of corner cases that are occurring when there is too much defocus. So that's it for the use case I wanted to show today. So Patrice, I don't know if you want to say the last word for the wrap up.
I will let you wrap you up and just compliment if you.
Okay. So today we present you the simulation tool that we developed. So first, but I will go fast on that, we show that this tool can simulate accurately a physical module. So we are below, the error is below the range of module to module deviation, which was crucial for us. We don't want to be just close to nominal data. We also have a flexible and adaptable tool. We can really adapt the type of input to the type of user and the type of data that we have at the beginning of a project. We can also enable compatibility with existing hardware or software. So for example, we already talked about that, but a user can definitely plug its own ISP model if he has one. So it's also completely standalone, but compatible with other tools. We often talk about optical design tools. Many optical designers are using the same, so we can directly simulate out of data from those optical design tools. And so through the different use case that we presented today, the goal was really to show how we could really save time and effort in defining what are the best specifications for a vision system when we start a project with application KPI. So on my side, that's it. I don't know if you want to add something, Patrice.
No, I think that you did it great, and the purpose and our main goal is always to save time, money, and effort for our customers. So just to mention that we use this tool internally to predict the outcome of our project since 15 years, but now we are in the process of releasing these tools to the market. So that's also something that I would like to mention. I don't know if there is additional question or.
So you just said you're releasing the tool to the market, meaning you would sell the simulation tool and support it for other people to run it?
That's our ambition. So actually, now we are at the phase. So we keep it internally for a long time, and now we are at the stage where we are discussing with early adopters of this tool, and with the ambition of selling it out on the market.
Great. So there is another question that came in the chat. Is the simulation mainly designed for automotive cameras, or is it also applicable to normal consumer cameras like a cell phone camera?
No, actually, it's true that we have a lot of examples that show automotive examples, but it's mainly with the current input scene data bank that we have. But obviously, like we also worked for different type of camera. We worked a lot on developing consumer electronic camera, like laptop camera, for example. So that's really adapted to any kind of vision system.
Are there any other questions from anybody? I know most of them were during the talk, but any follow-up questions?
Sure. I mean, I have one, maybe a general question. Jen, I guess I was thinking of what do you see as the next challenges? For example, simulation of, say, HD capture, multiple exposures, that sort of thing. As sensors get more complex, are you asked by your customers or potential customers to simulate that? For example, visible and combining infrared, for example, that sort of thing. Or is this next step?
Yeah, so actually all the steps that you mentioned were already asked to us. We have a roadmap that is super long, so it's now a question of priority. But for sure, like refining the sensor simulation, enabling the HDR parts is something that is frequently asked. Different wavelengths as well, so working in the thermal, for example. Something that we definitely want to improve, but more for maybe not for the simulation accuracy, but more for the user experience, is the way that we generate input scene. So you see right now we have limited data. That's why it was mainly automotive examples, but we would like to develop a more user-friendly option for the input.
Sure. With all of the things that I mentioned, wisdom is knowing what to take on first, of course.
Exactly.
Yeah, that's the main challenge actually. So it's selecting the one that is the most in demand and promising for the success of this tool. So that's the main challenge.
Yes, very good. Thank you.
I have a comment. You use Imatest quite a bit, and I'd be very happy to work with you to extend the use of Imatest in several ways. My biggest interest currently is the measurement of information capacity of the images. And information capacity is affected by both sharpness and signal-to-noise ratio. So it tells you a lot about how things perform as you go down into very dim light. Well, I'll be very happy to talk to you about how to add it. Really quite simple. And you can use the same test chart image. Will you people be at the Electronic Imaging Conference?
Yeah, actually, we will be giving a talk at Electronic Imaging. And,
good.
And actually, at Photonic West yesterday, I also talked with one person from Imatest as well, and we talked about exactly the same thing. So we already initiated that.
My son is visiting Photonics West.
Yeah, I
look forward to meeting you there, and Peter, and anyone else who's there. Okay. Yeah, I think we can perhaps do some work together.
Yeah.
It'd be very
Yeah.
interesting.
Yes, yes, clearly that what you're talking about would end up being a KPI, particularly an additional requirement, MTF, signal to noise, and so forth. So it's a natural fit, isn't it? That's good.
Yeah.
Yep.
Yeah. Right now, in terms of image, like for software validation, like computer vision validation, it's easy to have KPI, like accurate KPI. For human vision application, it's more challenging. So right now, we enable to directly measure the MTF on the image. But it's true that a more complete metric to be integrated in the tool would be for sure better.
Very good. Thank you
Julie,
very much.
yeah, let me ask a question. If you go back to the distortion example, it's not very often I have access to a wide-angle lens expert. You showed how you could do two forms of distortion correction. One which showed the center of the image, brought out the detail in that, and then another one showed the edges. Was it a requirement that the field of view remain circular in all cases? Because is it possible to fit this all into one output, right? If you give up a fisheye view.
So
Actually,
you can.
sorry. No, so actually we selected this view because that show you the behavior of the lens, the circular image. And after that, the sensor crop the way the field of view, and usually people crop the top, bottom, left, and right of the image, and you image only I would say the rectangular part inside the image circle. So I would say it's independent, but with this view you can see I would say the image footprint coming out of the lens. I don't know if that answers to your question or.
So when I've done this, usually it's in the context of stitching images, so they need to be in the same space. And so having two different kinds of distortion correction would make stitching impossible. And so I've always done this step where I've gone from this step to a spherical projection. And then from that, I can stitch images together or do ranging measurements and that kind of thing. And when I do that, and an image like this, it comes out like a bow tie, right? Because the edges get stretched more than the center, and you end up with this bow tie shape. And I was curious if you weren't constrained to the circle and you could allow different shapes, could you put both of these representations on the same in the same image, or was it a constraint in this design that you had to keep a circular field of view, a fisheye look?
So I think it's because what you propose to do is a transformation through software, which is here what represents is really like the lens image. So we cannot really combine both of them because each of the image represents a different optical system.
And to pick the example of camera stitching, we did that multiple times actually for customers. So when you stitch two camera back to back, you are with traditional wide angle lens, like you mentioned fisheye, you were lacking of resolution toward the periphery of the field of view. Exactly where you stitch the images with software. So that's why we designed the lens with this specific distortion and we call that panomorph because we increase the pixel density toward the stitching area, so on the side of the field of view, easing the process of stitching because you have more pixel density at the corners or at the edge of the field of view. Plus, since you have higher pixel density, you have higher image quality. Then when you stitch the two images, you remove this unpleasant stitching area because you have more information to play with the software. I don't know if that I made myself
very good.
clear.
That's a great explanation. Thank you.
Yeah.
Well, thank you very much.
Yes, thank you very much. And with all the applause and icons floating through our scene, it's highly appreciated. It's a very great talk, and thank you very much for giving the presentation.
Thank you for attending, and thank you for the opportunity.